Let's recall that in the previous video we saw three examples in which we exhibited that there is a problem that one encounters in this situation. Consider this ordered set X with some ordered relation in the ordered topology and let Y be a subset of X. Then there are two natural topologies we can impose on Y. One is the subspace topology that Y inherits from the ordered topology that's already there on X, and the other topology is that Y itself has its own ordered topology. Being a subset of X, Y itself becomes an ordered set, so it has that ordered topology. These two topologies are not necessarily the same. Sometimes they are the same, sometimes they are different, and that's what we saw in those examples. But today we are going to see that if we impose a particular restriction on Y, then these two topologies will always be the same. And that condition comes in the form of this definition. So we again, now this time we write everything. Let X comma less than be an ordered set. Then a subset Y of X is called convex in X if for any two elements A and B in Y, this open interval determined by A and B and which consists of all points X in X in that larger set such that A is less than X and X is less than B, if this open interval is a subset of Y. If this happens for any two elements A and B in Y, then we say that Y is convex in X. And this is something you can check very easily, that intervals and rays in X are convex sets in X. You may note one more subtle thing about this definition. What will happen if B is less than A, or say A is equal to B? In that case, this interval will be empty. So that anyway is a subset of Y. So the main part of the definition is that for those pairs of elements A and B where A is less than B, this interval has to be a subset of Y. If that happens, then we say that Y is convex in X. And this is today's result, theorem 16.4. So again, the same setup, let X comma less than be an ordered set. In the ordered topology, actually it's there in the text, but I forgot to write it. Be an ordered set in the ordered topology. And let Y be a subset of X which is convex in X. Then the ordered topology on Y is the same as the topology that Y inherits by being a subspace of X. So let's now prove this result. This is not how the proof starts in the text. The author has not used any names for these topologies, but for convenience we name them. Let tau O, this is O, okay, and tau S be the ordered topology and subspace topology on Y respectively. Now next what we do, next we consider this ray in X, A comma plus infinity, where of course it's understood that A is some point in X. Alright, now this point A may or may not belong to Y, the subset Y. If A belongs to Y, then the intersection of this ray with Y of course would be this set. It will be the set of all points X in Y which are greater than A, and which by its very form is an open ray in Y. Why are we able to say this? This is because A belongs to Y. So just like this is an open ray in X, this is the corresponding open ray in Y, A comma plus infinity. The only difference between this one and this one is that it consists of all points in X which are greater than A, whereas this one consists of all points in Y which are greater than A. Now what will happen if A is not an element of Y? We have seen this case, and now let's see this case. Then the author says that then A is either an upper bound or a lower bound for Y in X because Y is convex in X. But why? What is the reason for that? To understand that, we have drawn this schematic diagram. where this line represents x. This is not how x actually looks. I mean, you understand that it just is drawn in a way as if it's say that like the real line, where there is an order and points increase in this direction. All right. Now this is our a, suppose, which is not in I. Y is also here on this line somewhere. A is not in y. That's the condition. Now what if this is not true? That a is neither an upper bound nor a lower bound for y. Well, then a not being an upper bound means what? That at least one element of y will exceed a, will be greater than a. So that way we find an element c in y. Also, a is not a lower bound for y. So you will also find an element in y, say b, which will be less than a. But then what's happening? You have found two elements b and c in y, right? Such that a lies between them. But y is convex. So the open interval determined by b and c in x, that means all the points between b and c which lie in x, because y is convex, this needs to be a subset of y. But a is inside this open interval, so a then would have to be in y, which will clash with this. And that is why this situation cannot happen. A needs to then either be an upper bound or a lower bound for y in x, that is why. And this is the conclusion we draw from all this. In the former case, this intersection of y with the ray a comma plus infinity is empty, and in the latter case, this intersection is equal to y. Let's see more closely. The former case is where a is an upper bound for y, which means that say a is here, y will lie to the left of a. I mean in the sense of this diagram, because things are increasing in this direction, so a being an upper bound will lie to the right of y. And at the same time a is not in y, so this ray is entirely on this side, y lies entirely on that side, so there is no intersection. That's why the intersection is empty. Whereas if a is the lower bound for y, then y lies on this side of a. So obviously this intersection will be y, because y is a subset of that ray. So after this we have written some things. We are coming to that afterwards. Let's stop here for a moment and see what we have achieved, or at least what we have seen so far. We have seen that this intersection is either empty set or y or an open ray in y. And now we start again from here. Similarly, if you consider these other intersections, where this time you consider rays of this type, minus infinity comma a, and intersect them with y, that will also be either empty set or y or an open ray in y. And then this is our conclusion about this entire situation. That is, all sets of this form and this form belong to tau O, the order topology on y. Why? Well, that is because all of them are of these three types. Each one of them is either the empty set or y or an open ray in y. And these are open sets in the order topology on y. Empty set and y are open by the definition of topology, and open rays in y are again by definition of order topology open in the order topology. Alright, but at the same time, these sets, all sets of this form and all sets of this form, they form a subbasis for tau s, the subspace topology on y. Why? If you forget for a moment this intersection y parts and only consider these open rays, these two types of open rays when taken together, I mean all of them, all open rays of this type and this type, when taken together they form a collection which is a subbasis for the order topology on X. So by the definition of subspace topology, if you take their intersections with Y, then also you get a collection that becomes a subbasis for the subspace topology on Y. That's what we have written here. And that just simply means that tau S is a subset of tau O. Or if you want to use that terminology which we saw earlier, tau O is finer than tau S. Exactly why this is happening? This is happening because all these subbasis elements for tau S are elements in tau O. So their finite intersections will all belong to tau O, and so arbitrary unions of finite intersections will also belong to tau O, and those unions are what the open sets in tau S are, that is the elements in tau S are. That is how this is a subset of tau O. Now let us try to show that. Try to show means let's see what the author has done, that the reverse inclusion is also true. Conversely, you take any element B in Y, and for any such element you consider this open ray in Y determined by B, which is the set of all elements in Y which are greater than B. So it is the ray B comma plus infinity in Y, and that obviously is equal to the corresponding ray in X intersection Y. Similarly, the ray, this is also an open ray in Y, but this time we have all the elements which are less than B. So this is the minus infinity comma B, that ray in Y. That's the intersection of the corresponding ray in X and Y. So because of this fact, any open ray in Y belongs to tau S. This is one type of open ray in Y, this is the other type of open ray in Y. Each one of them has been found to be the intersection of Y with open rays in X. So by the definition of subspace topology, each one of them, actually these are not just two rays but two types of rays. There may be many such rays of both types. Each one of them belongs to the subspace topology tau S, that means open in the subspace topology. And next we consider this, since these open rays in Y form a subbasis for tau O, which we already know, that is why tau O is coarser than tau S, because all these open rays we have seen just now belong to tau S. So all their finite intersections, all possible such intersections will also belong to tau S, and arbitrary unions of those intersections will also belong to tau S, because tau S is a topology. But those unions are precisely the elements of tau O. So that's why we have this containment. Now combining this one and the previous one, which is its opposite, you have equality. That means the two topologies are the same. So this is what we have seen in this result, that if you have an ordered set X in which you have a convex subset Y, then the order topology and subspace topology on Y match. They are the same, which is not true in general as we saw in those examples. And because of this, the author has decided, or maybe this is the convention, that if you have an ordered set X and a subset Y of X which is not necessarily convex, and nothing is said about what topology we are imposing on Y, we should assume that it has the subspace topology. If we want to mean that it has the order topology, we have to explicitly say so.